Parallel computing using HIP, or Heterogeneous-Compute Interface for Portability, enables efficient programming across different hardware. It provides a programming interface for parallel computing, allowing synchronization, stream management, and memory allocation. HIP facilitates kernel optimization, profiling, and supports multi-GPU programming, with HIP plus message passing interface, enhancing performance and scalability in complex computational tasks. HIP, or Heterogeneous Compute Interface for Portability, is a C++ runtime API and kernel language. It enables developers to write portable code for AMD and NVIDIA GPUs. HIP provides a path for developers to migrate CUDA code to run on AMD hardware, ensuring performance and compatibility across different platforms. HIP, or Heterogeneous Compute Interface for Portability, is a C++ runtime API and kernel language. It enables developers to create portable applications that run on both AMD accelerators and CUDA devices. HIP provides a common programming interface, facilitating seamless development across different hardware platforms. HIP, or Heterogeneous Compute Interface for Portability, is a C++ runtime API and kernel language. It enables developers to create portable applications for both AMD accelerators and CUDA devices. HIP represents AMD's effort to provide a unified programming interface compatible with both CUDA and ROCm environments. HIP is open source, providing an application programming interface for graphics processing unit acceleration on both advanced micro devices and compute unified device architecture devices. It is syntactically similar to compute unified device architecture, allowing most compute unified device architecture application programming interface calls to be converted in place. HIP supports a strong subset of compute unified device architecture runtime functionality, enabling developers to create portable applications using a C++ runtime application programming interface and kernel language. HIP and CUDA share syntactic similarities, making porting straightforward. For memory allocation, use HIP malloc instead of CUDA malloc. Kernel launches in HIP require HIP launch kernel GGL, differing slightly from CUDA's syntax. Compilation also varies. Use HIPCC for HIP, compared to NVCC for CUDA. These differences highlight the need for careful attention when transitioning between the two platforms. When writing SHIP or porting from CUDA, note that AMD GCN hardware uses a warp size of 64 called wavefronts. HIP uses flat addressing with unified virtual addressing enabled by default. However, dynamic parallelism and CUDA 9 plus thread-independent scheduling are unsupported. Shared memory and registers per thread differ between AMD and NVIDIA hardware. The HIP API offers comprehensive device management with functions like HIP set device and HIP get device properties. Memory management is streamlined through HIP malloc and HIP mem CPY. Stream operations are handled by HIP stream create and HIP synchronize, while events are managed using HIP event create and HIP event record. Device kernels utilize HIP launch kernel GGL, and error handling is facilitated by HIP get last error. Kernels are functions executed on the graphics processing unit, launched from the host code. Memory management involves allocating, transferring, and freeing memory between host and device. Host code structure includes setting up device properties, managing memory, and launching kernels. Efficient host code ensures optimal graphics processing unit performance by synchronizing operations and handling errors effectively. In AMD GPU terminology, a compute unit is a parallel vector processor. A kernel is a function executed by multiple parallel workers. Threads are individual lanes in a wavefront, which consists of 64 threads executing in lockstep. Workgroups, akin to CUDA thread blocks, are groups of wavefronts within the same compute unit, enabling synchronization and communication. HIP kernel language provides essential qualifiers like _device_, _global_, and _shared_ for defining kernel functions. Built-in variables such as threadx.x and blockatx.y help in identifying thread and block indices. Vector types like int3 and float2 are used for data manipulation. Math functions like square root and power of f, along with intrinsic functions for synchronization and memory management, are crucial for efficient parallel programming. In HIP, kernels execute on a 3D grid, an abstract concept useful for mapping problems. AMD GPUs support 1D, 2D, and 3D grids, though 1D is common. Each grid dimension is divided into equal-sized blocks composed of multiple threads. These threads perform the actual computations. The grid and block structure in HIP is akin to CUDA's. In HIP, CUDA, and OpenCL, the grid organizes computation. In HIP and CUDA, a grid consists of blocks, each containing threads. OpenCL uses NDR range, with work groups and work items. Threads in HIP and CUDA are akin to work items in OpenCL, while warps in CUDA correspond to wavefronts in HIP, forming subgroups. In a 1D grid, each thread accesses its block via block_edex.x and identifies itself with thread_edex.x. The block's size is given by blockdim.x, while griddim.x provides the total number of blocks. This structure allows efficient parallel processing by organizing threads into manageable blocks. In 2D grids, each block and thread has a two-dimensional index, allowing for more complex data structures. Threads access their block IDs via blockindex.x and blockindex.y, and their thread IDs with threadindex.x and threadindex.y. This structure is crucial for efficiently managing parallel computations across two-dimensional data arrays. A simple parallel loop can be translated into a GPU kernel using the global attribute. Each thread computes a global ID using its unique thread and block IDs. Kernels should be declared void, and pointers must point to device memory. Threads execute the kernel's body simultaneously, potentially exceeding n threads in the grid. Kernels are launched from the host using a specific syntax. Define thread and block dimensions with dim3, then use hiplaunch kernel ggl to execute the kernel. Specify grid and block dimensions, dynamic local data share space, stream, and kernel arguments. This is similar to Compute Unified Device Architecture's syntax, ensuring efficient parallel execution on the graphics processing unit. Blocks and threads are essential for mapping kernels to hardware. Blocks are scheduled onto compute units, with all threads in a block executing on the same compute unit. They share local data store, memory and L1 cache. Threads execute in 64-wide chunks, called wavefronts, on SIMD units. Optimal block size is a multiple of 64. The host allocates memory in VRAM using hipmalloc, recording a pointer to device memory. For example, allocating 1000 doubles requires calculating the size in bytes and using malloc for host memory. After processing, free the host and device memory with free and hip-free respectively, ensuring efficient memory management in device kernels. Efficient data transfer between host and device is crucial. Use hipmem-cpy for copying data, host to device to host, or device to device. For strided array sections, hipmem-cpy2d allows specifying destination and source pitches, bytes per row, and number of rows. This flexibility optimizes memory operations, enhancing performance in complex data structures. HIP API functions return error codes of type HIP_error_t, such as hipmalloc and hipmem-cpy. Successful operations return HIP success. Otherwise, an error code is provided. Use hipgetLastError or hippeakLastError to retrieve the last error. For debugging, hipgetErrorString translates error codes into readable messages, aiding in identifying issues efficiently. Integrating error checking with GPU programming requires careful adaptation. Use HIP API functions to manage errors effectively, ensuring HIP success for smooth execution. Transition CPU code to GPU by rethinking algorithms and optimizing data reuse. Manage data transfers between CPU and GPU to avoid bottlenecks, ensuring efficient kernel execution and high hardware occupancy. Graphics processing unit programming involves executing numerous small tasks via kernel calls, often replacing loop iterations. Adapting central processing unit code for graphics processing unit requires rethinking algorithms to fit the execution model. Reusing data on the graphics processing unit is crucial for high hardware occupancy. Careful management of data transfers between central processing unit and graphics processing unit is essential to avoid bottlenecks. Kernels operate on a three-dimensional grid of threads, partitioned into equalized blocks. This grid organizes the workload with dimensions set at kernel launch. Within a kernel, built-in variables like threadx, blockatx, blockdim, and griddim are used to manage and distribute tasks efficiently across the graphics processing unit. Kernels are device functions executed by the graphics processing unit, declared with double underscore, global underscore, or double underscore device underscore attributes. They must be void type, and pointers passed should point to device accessible memory. Unique thread and block IDs help distribute work efficiently across the graphics processing unit, ensuring optimal performance and resource utilization. Heterogeneous computing interface for portability synchronization ensures proper execution order and data consistency across graphics processing unit operations. Streams allow concurrent execution of tasks, enhancing performance. Radeon Open Compute 4.50 introduces direct dispatch, optimizing task queuing and synchronization by directly queuing packets to the asynchronous queuing language queue, unlike previous versions that used a queue per stream. A stream in heterogeneous compute interface for portability is a sequence of operations executing in issue order on the graphics processing unit. Operations in different streams can run concurrently. Radeon Open Compute 4.50 introduces direct dispatch, directly queuing packets to the architected queue language queue, enhancing synchronization. Previously, Radeon Open Compute used a queue per stream, limiting concurrency. A stream in HIP is a task queue, executing tasks like kernels and memcachs in order. Different streams can overlap, sharing resources, create streams with HipStream create, and destroy with HipStream destroy. Using 0 or null as HipStream T runs tasks on the null stream, where tasks wait for all other streams to complete. Blocking calls like HipMemsPy use this stream. In HIP, concurrency is managed through streams. By default, only a single stream is used unless specified otherwise. Commands within a stream are synchronized, except for asynchronous calls and kernels, which can execute concurrently. This allows for efficient resource utilization and improved performance in parallel computing tasks. The Stream/Events API in HIP allows for efficient GPU resource management. Use HipStream create to initiate an asynchronous stream and HipStream destroy to terminate it. Events can be managed with HIP event create, HIP event record, and HIP event synchronize to track execution. Measure execution time with HIP event elapsed time and clean up with HIP event destroy. Executing multiple small kernels in a null stream results in serial execution. By assigning each kernel to a separate stream, such as stream 1 to stream 4, we can utilize the GPU's compute resources more efficiently. Ensure kernels modify different memory parts to prevent data races. Note that overlapping computations may not enhance performance for large kernels. Streams can also overlap kernels with data movement. Advanced micro-devices graphics processing units have separate engines for host-to-device MEMCPIs, device-to-host MEMCPIs, and compute kernels. These operations can overlap without dividing graphics processing unit resources if placed in separate non-null streams. Ensure host memory is pinned for optimal performance. Host data allocations are pageable by default, but pinning allows direct graphics processing unit access. Allocate pinned memory using HipHost malloc and free it with HipHost free. Pinned memory significantly boosts host device memory copy bandwidth, making it essential for frequently transferred data. Using streams in HIP allows for concurrent execution of data transfers and kernel launches. By employing HipMemCPy async and HipLaunch kernel GGL with distinct streams, we can overlap data movement and computation, enhancing performance. This approach efficiently utilizes GPU resources, reducing idle time and improving throughput for multiple kernels. Switching to asynchronous memory copies and streams enhances performance. Use HipMemCPy async for data transfer, specifying unique streams for each operation. Launch kernels with HipLaunch kernel GGL, associating them with their respective streams. This approach allows overlapping of data transfer and computation, optimizing resource utilization and reducing execution time. In HIP, efficient data transfer and compute can be achieved using streams. By employing HipMemCPy async for asynchronous data transfers and HipLaunch kernel GGL for kernel execution, we can manage multiple streams. This approach allows for overlapping computation with communication, enhancing performance by executing kernels on different streams simultaneously. Utilize streams to overlap computation with communication by creating multiple streams using HipStreamCreate. Implement asynchronous data transfer and execute kernels on different streams with HipLaunch kernel GGL. This approach enhances performance by efficiently managing resources and reducing idle time during data processing. HipDevice synchronize is a heavy-duty sync point, blocking the host until all device streams complete. For specific stream synchronization, use HipStreamSynchronize stream. Events offer finer control. Create with HipEventCreate, record with HipEventRecord, and synchronize with HipEventSynchronize. Use HipStreamWaitEvent to make streams wait for specific events, ensuring precise task ordering. HipEventSynchronize event blocks the host until the event completes, ensuring synchronization within its stream. Use HipEventElapsed time, end time, start event, end event to measure time between events, aiding in performance analysis. HipStreamWaitEvent, stream event, allows non-blocking host operations, enforcing task ordering across streams by waiting for event completion. In GPU computing, streams efficiently manage message passing interface traffic. First, queue the local compute kernel using HipLaunch kernel GGL. Then, asynchronously copy halo data to the host with HipMemCPy async, followed by HipStreamSynchronize to ensure data arrival. Exchange data using MPI data exchange, and finally, send updated data back to the device with another HipMemCPy async. Utilizing a GPU-aware MPI stack, host arrow device traffic is minimized. Synchronize GPU data readiness with HipDevice synchronize. Exchange data directly using MPI data exchange with device pointers. Launch compute kernels with HipLaunch kernel GGL, ensuring efficient execution. Finally, use MPI wait to confirm request completion, optimizing data flow and computational efficiency. The reverse kernel utilizes shared memory to reverse an array of doubles. Each thread copies data to shared memory, ensuring synchronization with notch sync threads. This barrier guarantees all threads reach the same point before proceeding, allowing the array to be written in reverse order efficiently. HIP, or Heterogeneous-Compute Interface for Portability, provides a C++ runtime API and kernel language that allows developers to create portable applications. It enables efficient synchronization within kernels, crucial for ensuring data consistency and correctness across threads. Understanding HIP's synchronization mechanisms is essential for optimizing performance in parallel computing environments.